Welcome, science hunters! In our previous video, we explored how to utilize linear motion when throwing a punch by delving into the physics of linear motion. In this video, we will learn about the physics of rotational motion, another fundamental area of classical physics, and apply this knowledge to our punches. Before we begin the hunt, I'd appreciate it if you like the video and subscribe to my channel. Enjoy watching. Rotational motion is divided into two types. The first is spin motion, which is rotation around itself, and the second is rotation around a central point. Rotation around a point means that this point acts as the center of rotation. In self-rotation, however, the center of rotation is the object's center of mass, and the rotational energy is provided by the object itself. Rotational energy arises when a force is applied at a point offset from the object's center of rotation. For an object rotating around itself, the center of mass serves as the center of rotation because the motion is balanced around this point. Now, let's explore what the center of mass is. The center of mass is the point where the sum of the products of each mass in an object and its distance from this point equals 0. Thus, the center of mass is also the point where an object behaves as if its entire mass is concentrated. Physically, this point is crucial for an object to remain balanced and to define its motion. To make an object rotate, a force must be applied at a point other than its center of mass. Since the center of mass affects a person's ability to maintain balance, we will focus on this concept extensively in our video on the science of stances in martial arts. From our explanation, we can deduce how to calculate the center of mass. The center of mass is a point within the object, meaning it is a position vector. Therefore, for a three-dimensional object, it is a vector in 3 dimensions. The center of mass is calculated separately for each dimension. This calculation involves summing the products of all individual masses and their positions in each plane, and then dividing by the total mass of the object. We will understand why the center of mass serves as the center of rotation when an object spins around itself once we learn about torque, the physical quantity responsible for rotational motion. To make this concept easier to grasp, let's consider a thin rod fixed at one end. If we apply a force directly toward the center of rotation, the rod will not rotate. However, if we apply a force that does not pass through the center of rotation, the rod will start to rotate. When the rod rotates, different points along its length will travel different distances in the same amount of time, depending on their distance from the center of rotation. This means that distance must influence the effect of a physical force applied to the object. Because of this, a new vector quantity known as torque was derived from the cross product of the force and distance vectors. Torque is defined as the physical quantity that causes an object to rotate. Just as linear motion results from force, rotational motion results from torque. The rate at which the angle of a rotating object changes over time is determined by its angular velocity. Change implies differentiation, and the direction of this change is given by the cross product of the unit vector in the direction of position. The reason for using the cross product with the unit vector in the direction of position is that it simplifies the derivation of other physical quantities. This is a matter of definition. The vector product of the angular velocity vector and the position vector gives the linear velocity vector. Linear momentum is a physical quantity resulting from the product of velocity and mass. We found the velocity vector with respect to the angular velocity, and if we use this equation for linear momentum, we get the following. As seen from the momentum equation, the greater the mass, the lower the velocity. In other words, mass is the resistance to changes in motion. Similarly, rotational motion also exhibits resistance to change. This resistance depends on both the mass and shape of the rotating object because the center of mass varies with the shape of the object. The resistance to changes in rotational motion is called the moment of inertia. It depends on how mass is distributed across the object and its shape. Therefore, it is calculated as follows. Linear momentum is the product of velocity and mass. Angular momentum is the product of angular velocity and the moment of inertia, which is the resistance to the change of this velocity. Just as force is the change of linear momentum with respect to time, torque is the change of angular momentum with respect to time. Thus, torque is equal to this. In the linear punch video, we saw the importance of energy in collisions. Now, let's determine rotational kinetic energy and power, and ultimately understand the significance of rotation in punching. Kinetic energy is found by integrating the force applied along a path. For a rotating object, if we replace force with torque and path with the angle rotated, we obtain rotational kinetic energy. In the case we want to examine, the moment of inertia does not change with respect to time, since the mass and shape of the object will not change, so we can ignore the first term in the integral. This equation gives the energy of a rotating object. When this rotating object collides with another, the energy transferred can be the same regardless of the collision duration, as we saw in linear collisions. However, the effect can differ, which is why we need to calculate power, a key physical quantity. In this case, angular power is given by. This equation fully reveals what happens when a rotating object collides. The power exerted by a rotating object with a certain angular velocity upon hitting a stationary object depends on the change in angular velocity, the shape and mass of the rotating object, and the distance of the impact point from the center of mass of the stationary object. These are crucial insights because we will use this knowledge when throwing a punch using rotation. Now that we've clarified many aspects of rotational motion, we can apply this knowledge to improve punching techniques. Let's analyze the hook punch, a fundamental technique where rotational motion plays a key role. The hook punch is a technique in which the fist travels in a curved motion from the side inward to strike the target. Rotation occurs at 3 different points. The legs rotate the body, the torso rotates the shoulders, and the shoulders rotate the arm. This generates rotational kinetic energy at multiple stages. The energy is then transferred through the elbow, bent at 90 degrees, and finally delivered to the target with a solid punch. Let's first analyze how these 3 rotation points contribute to maximizing rotational kinetic energy. Starting with the legs, the punching side leg is positioned behind while the other leg is placed forward. The knees are slightly bent, with the front foot pointing toward the opponent and the back foot angled outward to maintain balance. The back leg pushes the body, allowing the fighter to rise onto the toes and straighten the knee, reinforcing the rotational motion. The torso leans slightly to the side, keeping the punching arm at the back. This positioning allows the body to rotate through a greater angle, maintaining acceleration for a longer time and increasing angular velocity. A higher angular velocity leads to greater kinetic energy, which is then transferred to the shoulders. The shoulders play a crucial role in delivering the final rotational energy. The punching arm starts behind the body. As the body rotates, the shoulder follows through, guiding the punch toward the target. This alignment not only enhances precision, but also maximizes rotational energy transfer to the punch. The rotational kinetic energy gathered from these points must be transferred to the target with an appropriate arm and wrist position. Otherwise, everything will be wasted. Therefore, as the next step of the technique, let's hunt the position of the wrist and arm. As we see from the angular power equation, the farther the impact point is from the center of mass, the greater the torque, and consequently, the power increases. This might make us think of throwing a punch with a fully extended arm. However, in this case, the risk of injury is high, and if you strike from a far radius, the punch will take longer to reach the opponent due to the greater angular travel. This gives the opponent more time to defend. Therefore, balance must be maintained. To achieve this, we should keep the angles of the front arm and rear arm at 90 degrees while ensuring a firm wrist position. This allows the punch to reach the target with maximum force. In this position, we should maximize the radius between the center of mass and the impact point. To do so, the shoulder, arm, and fist must be at the same height, meaning they should be aligned. This ensures the maximum radius. Finally, the position of the fist upon impact is crucial. When throwing a hook punch, the fist can be positioned either vertically, thumb up, or horizontally, thumb inward. A vertical fist provides a more solid and controlled strike at close range, while a horizontal fist offers better rotation and protection for longer-range hooks. The choice of technique depends on personal comfort and fighting style. Rotational motion plays a crucial role in many areas, from daily life to martial arts. To throw an effective punch, it is essential to understand how angular momentum, moment of inertia, and torque work. Especially in techniques like the hook punch, we can generate power by maximizing efficiency from body rotation, torso movement, and the angular velocity of the arm. By applying physics in martial arts, it is possible to develop stronger and more effective movements. In the next video, we will analyze more complex techniques by utilizing both linear and rotational power. Don't forget to subscribe so you don't miss it. See you soon!